We're going to see the demonstration of text clustering. First of all, we will see how do I calculate similarity score based on cosine, Jaccard, Euclidean and Manhattan distance. Then we will also see how do we calculate Bigram score. I'll demonstrate k-means, hierarchical clustering, how do we do silhouette score calculation, and then also we will check Brown clustering. So initially, let us check how do we calculate cosine and Jaccard similarity. Consider if I have two sentences. My house is empty. There is no one at mine. I'll perform TF-IDF vectorizer, and I'll call the cosine similarity to be calculated, and also Jaccard similarity to be calculated. Now Jaccard similarity has been defined here as a function here. So this is the utility function which will help me to evaluate the Jaccard similarity, and cosine similarity can be calculated using the inbuilt function. So here A, B, C are there. A indicates the number of words in document 1, the number of words in document 2. C is the common words, and so A plus B minus C will give me the denominator. So this is the cosine similarity and the Jaccard similarity between the two words. Now let us see how do we calculate a simple k-means problem. How do we calculate a simple k-means problem using document clustering? So I love playing football on the weekends. I enjoy hiking and camping in the mountains. I like to read books and watch movies. I prefer playing video games over sports. I love listening to music and going to concerts. Now these are the 5 sentences that we have. Initially we perform TF-IDF vectorizer for this, and I want to define them into 2 clusters. And so here I say K means I'm looking for 2 clusters for the data set that I give here, and here it has predicted that the second and the third sentence, I enjoy hiking and camping in the mountains, I like to read books and watch movies, belong to one cluster, whereas the other 3, I love playing football, video games over sports, I love listening to music and going to concert, is coming under one cluster. This is a simple way of how the cluster is defined. I can also calculate the silhouette score on these. So I can calculate the silhouette score. The silhouette score that I get is minus 0.002. I can also visualize the clusters here. Since we have TF-IDF, we can reduce the dimensions using PCA. So I will reduce the dimensions and I will get, these are the centroids of the 2 clusters. I have this point and this point belonging to one cluster, whereas this point and these 3 points belonging to another cluster. Now let us see what is the Levenshtein distance. This is again a simple example of what happens when we want to visualize. So I get the centroids and I get one cluster and the other cluster here in yellow. This indicates the centroid. Let us see the Levenshtein distance. So here I can calculate the Levenshtein distance using edit distance. So if I have if possible and possible, so these are the 2 words that I have, and here I get the Levenshtein distance between sentence 1 and sentence 2 as 4. So first of all, it is checking for the first one, which is length is 11, and the second possible dot, which is length is 9. So what are the changes that is required? So I has to be removed, f has to be removed, space has to be removed from the first one, and a dot has to be removed, or a dot has to be inserted here. So there are 4 changes that are required, and so there are 4 changes that are needed. So these 3 should be removed, 1, 2, 3, and a dot has to be added, and then I will get the 2 sentences similar. That is the edit distance between the 2. Here I am defining some functions like compute the vectors, just to get the count vectorizer object, computing the cosine score, and here I am computing the Euclidean score, and I have 2 sentences. It might help to study NLP if possible. It can help to play football again if possible. So for these 2 words, I am calculating the cosine similarity and the Euclidean distance. So I can see that the cosine similarity score between the 2 words is 0.589. So cosine similarity is checking between sentence 1 and sentence 1, sentence 2 and sentence 2, and then it is checking between sentence 1 and sentence 2. So it is the cosine similarity that I am getting between sentence 1 and sentence 2 is 0.589, indicating that 58.9% they are matching, and on the other hand the Euclidean distance is 2.64, indicating that they are not drastically distant, but they are somewhat apart. We can also calculate other other measures like Jaccard similarity, dice similarity, overlap coefficient. All these can be calculated for these same sentences. We can also calculate the Manhattan distance. Manhattan distance, see here I am getting 3 plus 4 plus 5, a Manhattan distance of 12. Now let us see how do we calculate the Bigram score. So now the Bigram score will consider the 2 distance apart. So for which I make use of Bigram collocation finder, Bigram associate measures, and the word tokenization libraries. So this is a sentence, and here I am checking the Bigram finder. I print all the bigrams that are there, as you can see. Is a, this is, a foo, car shape, red car, all are printed, and then it shows me what is commonly occurring. See, is a, this is the score, and here again this is a score. So this is appearing is a very common bigram, whereas is a is also a very common bigram, and these are the PMI scores of these bigrams. So PMI scores refers to the point-wise mutual information. Scores of these bigrams. Now we are going to consider the 20 news group data set. And this includes 20,000 newsgroup documents, and which are divided into 20 categories. We get the required packages, and here I am getting the news data. These are the functions which will help me to remove the stoppers, perform lemmatization, pre-process the entire text, and then I apply call this. So either I can make use of TF-IDF or word-to-vec, or glove can be used for capturing the semantic meaning, TF-I for vectorization of these. So here I make use of word-to-vec. Word-to-vec will help me to capture the internal meaning of these. Let me show you a news article, one sample news article that we download. One second. See, I have atheism, graphics, motorcycles, sport, baseball. Under science, I have cryptography, electronics, medicine, space. Under talks, I have politicals, within which there is guns, politicals, within which there is Middle East. Miscellaneous under politics, miscellaneous under religion. So these are the various 20 categories in news articles that is there. So this is the data that we have, and I get all the needed libraries, after which I make use of word-to-vec. I apply word-to-vec on these sentences, and then I calculate the average word vector. Once I get the average word vector, I apply that average word vector for each of the sentence and get the needed vector, and then perform PCA to reduce the dimensionality. After doing that, I am getting 18846 records with 2 columns. Applying the DBSCAN on this particular data, so initially I apply k-means, and I am getting, that is, in the category number 4 I have 681 articles, and category number 5 I have 1253 articles, and so on. See, these are the centroids, and these are the various 14 clusters that I am getting. And this is the count for each one. So count for each of the 20 categories, how many do I have under each. So here, as you can see here, I am applying for each of the cluster. It is printing the silhouette score also. It is showing me for each of the cluster what is the silhouette score. Let me show you this output. This is the data, and this is the silhouette score. And then there is the count. So here I am doing it for 7 clusters, 15 clusters, and 20 clusters. So I'm checking what happens if I have only 7 clusters. So 1, 2, 3, 4, 5, 6, 7 clusters. This is the 7 clusters. The silhouette score 0.38. This is with 0.36. This is the silhouette score. And with 20 clusters, I'm getting 0.369 as the silhouette score. Now I want to apply DBSCAN. Now what happens with DBSCAN is, I apply DBSCAN, and these are the various centroids that I'm getting. I have made use of 5 clusters here. Then I applied Agnes. Again, applying it for 7 clusters, and for 15 clusters I want to categorize this data. So here this is the output for cluster visualization for 7 clusters. This is the dendrogram for the 7 clusters. The silhouette score that I got is 0.33, and the count of articles in each of the cluster. Similarly, for 15 clusters, the same thing. The next is expectation maximization algorithm. So here again, expectation maximization works in 2 steps. It will compute the expected value of the hidden variables, and then in the maximization step it will re-estimate the parameter by checking the maximum likelihood of the data. So here Gaussian mixture is the library which will help me to do, and 7 and 15 clusters are again being used here, and this is the visualization of the 7 clusters, and the number of clusters is 7, and the silhouette score is 0.28, which is lesser, as you can see. So expectation maximization is not giving me a good output here with 15 clusters, and the silhouette score that I got here is 0.31. Then the next is Brown clustering. Now Brown clustering, as we already saw, it helps me. It is very similar to agglomerative clustering. So consider if I have these sentences here, I can make it into a bigram corpus and apply Brown clustering onto it. And here, as you can see, it helps me to cluster the words here. So bus, bar, shep and this come to one cluster. Car and A come to next cluster, and I have specified that I am looking for m equal to 4. So I am looking for 4 clusters. Whereas foo belongs to another cluster, red, blue is belong to another last cluster, and for each of these clusters I have also got one representation for the codes that are there. So this Brown clustering has helped me to categorize all the words into 4 clusters. So I had vocabulary count of 10, that is there were 10 unique words. Token count totally 21. 2-gram count I got 20, and then Laplace smoothing was performed, and these were the various word clusters that I got. So this is example of Brown clustering.